In this Calc 2 video, we're going to look at trig integrals. So what do I mean by trig integrals? In this case, we're talking about integrals that will use different trig properties or trig identities that will help us solve those integrals. So before we get started, there's some trig. Of course, at this point, I'm not going to write out the reciprocal functions. I'm hoping at this point you all understand. If not, take a moment to review your reciprocal functions, meaning, tan is sine over cosine, cotan is cosine over sine, secant is 1 over cosine. That's what I mean by reciprocal functions. The other thing, make sure you fully understand, is your Pythagorean identities. So I know you're all familiar, of course, sine squared, so cosine squared, x equals 1, but don't forget 1 plus tan squared x. And you want to be careful, you don't want to get them confused with the hyperbolic functions we did in 7.3. We're back to our standard trig functions now, not hyperbolics. And of course, tan squared plus 1 equals cosecant squared x. The other, we do these like power reducing. So in other words, how can I get something squared down to something that's not squared? So take a look at sine squared x is 1 minus cosine 2x over 2, and cosine squared x equals 1 plus cosine 2x over 2. So you will kind of want to take a look at and make sure you remember these sets of functions, and any other ones we come across the way, we'll make sure we highlight. So I try to present this in a way that you have to memorize the least amount possible. At the end, I'll show you some things you can memorize if you choose to go that route. I kind of prefer not to do all the memorization, because if you screw up memorizing something, that's going to screw up your whole test. But if you just know how to work through the integral, memorizing the least amount possible, I think that's helpful. In the end, you can make the choice you want to make. Please also, if you don't recall all of your derivatives and integrals, review them. Have the sheet in front of you. And what do I mean by that? Derivative of sine is cosine. Derivative of cosine is negative sine. The integral of cosine is sine, but the integral of sine is negative cosine. Make sure integral tan is secant squared. Integral cotan is negative cosecant squared. You do need to memorize these. So I don't want to give you more to memorize, because there's already a lot there you need to know. Derivative cosecant is negative cosecant cotangent. So take a moment. They're in your textbook, even if you need to go back to chapters 5, 4, and 5. Chapter 3 actually would have your derivative functions, and then chapter 5 will have your integral functions. And make sure you really know those trig integrals. That will help immensely. The other thing is we have this in calculus. And hopefully you recognize this last semester in Calc 1. We have these kind of calc-trig pairs. And you see it with your derivatives and your integrals. Sine tends to be always paired with cosine. Tan with secant, and cotan with cosecant. So in other words, when you take the derivative of tan, it's a version of tan or secant, and so on and so on. So that's important to keep in mind as well. There's this is all about, and this entire chapter 8 is learning various strategies on how to attack some integrals. I'm going to jump into doing problems. I will show you formulas you can certainly memorize along the way that are in your PowerPoint. But for the most part, I'll also show you how you don't need to memorize those formulas. So we'll start off with kind of different, simpler problems, and we'll progress our way down. Also, we're going to be utilizing our use of procedures and utilizing our integration by parts procedure. So we'll learn how to kind of separate trig functions so that, oh, it can be a u-sub, or yes, it can be an integration by parts. We'll start, let's just get started. Again, throughout this whole video, we're just going to go through a series of examples. So for the first one, let me take the integral of cosine, oh, let's go crazy, cosine to the 19x sine x. So anytime you're integrating, you don't want to go too crazy if it's simple, right? When we talk about something simple, I always start with, is there something else? Sorry, my watch is going crazy. I always start, I look at it and go, all right, number one, I got a product, so I have an issue. I can't just integrate and be done. I have this product, but is one just the simple derivative of the other? If that is the case, that's a u-sub problem, and we have that here. In other words, if I let u equal just plain old cosine x, do I have a du, or a version of du that I can easily get, du dx, in my integral already? Absolutely. Because the derivative of cosine is negative sine x dx, which you can clearly see is right there. Let me just get the negative in there so it fully is right there. If that's the case, you're done. This is a simple u-sub. So how do you recognize the simple u-sub? My exact derivative is right there. All right? So then I can just quickly finish this off by keeping the minus on the outside. U to the 19th du, which you all know will end up being negative u20 over 20 plus c. And since we're dealing with indefinite integrals, as we will most see throughout this particular section, is change that to negative cosine 20 to the 20th power of x over 20 plus c. All right. That was nice. So what happens now? Go back to the 19. I like 19. Let's go to 19. I change that, and instead of the sine, it now is a sine cubed x dx. I want you to recognize, that if I try to let u be cosine, I do not have the derivative of u. No, I don't have a sine, I got a sine cubed, which tells me, well, it's simply not going to work. So there's a lot of different ways to approach this, and it's not till you do a bunch of examples that it starts to make the most sense. But in this case, yeah, for that to work, so let's start to break it up a little bit. Yeah, I can't have sine cubed. I would need, well, a sine squared x times a sine x. Because to allow u to be cosine, I need a sine by itself. All right, well, that's not too bad. I can get a sine by itself by just breaking up sine squared, sine cubed into sine squared and sine, just sine. But that won't work unless this sine squared is actually in terms of cosine. So that's where you go to your little list and you think, oh, wait a minute, I can put sine squared in terms of cosine, right? So this might be able to go somewhere. So let me put what I have here so far. So I've got integral cosine 19x sine squared x sine x dx. All right, so that's cosine 19x. Sine squared is simply 1 minus cosine squared. Sine x dx. I'm actually getting somewhere. go ahead and let's distribute that across. Doesn't that give me cosine 19x, sorry, minus cosine 21x, all that times sine x dx. And you're thinking, well, why would that work? Oh, all I need is to identify in one of the products, right, a u, and then have a du over here. In other words, if I can now let u equal cosine x, du equals negative sine x dx, try it. U negative. Oh, I forgot my negative. I need my negative, which is over there. U to the 19th plus u minus u to the 21, sorry. And that's just du. If you don't like the negative out front, sometimes it's always easier to distribute it through and put it this way. It just makes life a little bit easier when you're integrating. I can integrate that. All right? U 22 over 22 minus u 20 over 20 plus c. And now I just need to replace with what u is equal to, which is cosine. Cosine 22x over 22 minus cosine 20x over 20 plus c. There's your answer. So all we really did is use our trig properties to do a little rearranging to get only cosines, because I know if I let cosine be u, I have my du because I've got my sine. Again, practice. You got to practice a bunch of these, and then those patterns will start to emerge. So we're just going to keep going. We're just going to keep trying a bunch of problems. Cosine cubed x, radical sine x. So radical sine x is actually sine to the 1/2 x. I like to take my radicals and automatically put them. Okay. Well, you kind of like the last problem. To do any sort of u sub, I need to have a single cosine or sine, right? It doesn't matter because they're derivative of each other. Well, it's kind of hard to get a sine and break up sine because that's to the 1/2, but can I break up cosine? If I break up cosine and make it cosine squared x times my sine, I need to have another cosine, right? So what we kind of say is, hey, wait a minute, there's my du, right? I'm getting closer. Du, because cosine's a derivative of sine. Now, even though I have a cosine and sine, we already found out in the last problem that cosine squared can easily be turned into sine squared. The same way sine squared in this problem was easily turned into cosine squared. So I can do that by simply making cosine squared 1 minus sine squared x times sine to the 1/2 x, keep my dx. All right, just keep in mind, that's going to end up at some point being our du. Let's distribute. It's always good to distribute it through. So that's the integral of sine to the 1/2 x minus just remember you have to add your exponents, so 2.5 is 5/2. This will now work out as a nice u-sub problem, right? We already know that's du, so we're going to let u equal just plain old sine x du. The integral of the derivative, derivative of sine x is cosine x dx. So I can rewrite it as u to the 1/2 minus u to the 5/2 du. I can easily integrate that just using power rule. If you can get back to power rule, life's just so much easier. So power rule, raise it, it's divide by 3/2 multiplied by 2/3. That goes up to 7/2. And last step, just plug your u back in. So it's actually 2 sine of 3/2 x over 3 minus 2 sine of 7/2 x over 7 plus c. And there's your answer. All right? So you can pause the video. I'm going to just keep going. If you need to see this a little bit more, just pause your video and go back. We're going to move on. All right. Now, here's the problem. Again, everything's working great. We did these two problems, worked out great. And then I get to something like this. Integral sine squared x cosine squared x dx. Well, if you try to do the same thing again, you're going to run into a problem. Here's what was nice about the problems, the previous problems we did. When we peeled off a cosine, we ended up with a cosine squared, and we had a nice formula for that. If you try to do that here for cosine or sine, doesn't matter, you're not going to be able to turn. So suppose we try to peel off a cosine to make our du. We're not going to be able to turn our cosine into a sine. Okay? I mean, if you peel off a cosine, you can turn your sine into a cosine, but it doesn't work because I won't have a sine peeled off. I have a cosine peeled off, so I have to get everything else in terms of sine. You're not going to be able to do it. You can try it. Not going to work. That's where these other formulas come in. And these are those power-reducing formulas. So these are the formulas I put at the top, the very first beginning of the video. And the one we're going to use is for cosine squared, the one that says, hold on. And this is the one that says cosine squared x. So what do you mean by power reducing? We're going to take a squared and we're going to turn it into something that's not squared, which is 1 plus cosine 2x over 2. And sine squared x equals 1 minus cosine 2x over 2. Now, here's what's nice when you do use these power-reducing formulas. They are both just cosine functions. So let's see what happens when we do this. Change sine squared to 1 minus cosine 2x over 2. And these are identities you did learn back in when you took trigonometry, which would have been pre-calc 2 at RVCC. This would have been called something else at another college. Now we just have a little algebra. We're essentially just multiplying two binomials together. If you don't see it, pull the 2's out. Pull the 1/2 here and the 1/2 here to 1/4. You can pull those out, and then you just have 1 minus cosine 2x times 1 plus cosine 2x dx. You're just multiplying, combining like terms. This is a sum and difference. And if you recall with sum and differences, right, 1 times 1, of course, is 1. When you multiply 1 times cosine 2x times 1 times negative cosine 2x, those middle terms will cancel away, and you end up with a negative cosine squared of 2x dx, which you're thinking, but wait, I've got another cosine squared. Well, not exactly, because to integrate a cosine squared, we would need a sine squared to do our u sub. We don't have that, but go ahead. Sometimes you got to do things multiple times. Change cosine squared of 2x using this formula. But here's the thing. In place of x, so if this is 1 plus cosine 2x divided by 2, then cosine squared of 2x equals 1 plus cosine of 4x divided by 2. So just be careful there, because your x is actually a 2x, so 2x times 2 gets you that 4x. So we have 1 minus 1 plus cosine 4x over 2. A lot of algebra here, meaning you got to combine those together. When I say combine those together, rewrite your 1 as 1/2, so you're combining 1/2 minus 1 plus cosine 4x. One-fourth. I don't know why I wrote 1/2 up there. You're making it as 2 over 2, so it combines. Sorry about that. It becomes 2 minus 1 minus cosine 4x all over 2 integral dx. So I can take the half out. I get 1/8 integral. 2 minus 1 is 1 minus cosine 4x dx. Here's the thing, why we need power reducing. Once you get it down to a trig integral of sine or cosine that is no longer being squared or cubed or anything else, you can take the integral. All right, so we have our eighth, and then we let take the integral, we end up with x we end up with here it is, let u equal 4x, du equals 4. Right, you need the 4, so you've got to put in, and you have your, oops, sorry, your sine for x, you're going to have to divide that by 4. Okay, so again, it's different techniques. These are called power reducing. You need to you can use them to take your trig functions that are squared and reduce them down. Let's keep going. So now let's take a look at if we don't have pairs. Remember we talked about sines and cosines are great together in an integrals and derivatives. Secants and tangents are great together. But what if we have a sine with the tangent. So we can change tangents into sines and cosines. That's the first thing you want to kind of look at. Can I change it so I get these calc trig pairs? Sure, tangent would be sine squared over cosine squared, so that would end up being sine cubed theta over cosine squared theta dx. Now, here's what I want you to notice. This is kind of nice. This is an odd. So if we take out an odd, that could help us, and it leaves us with sine squared theta over cosine squared theta. When I mean take out, we're kind of like sticking it, oops, it was a sine. We're putting it over here to possibly be a du at some point, right? Can we make that a du? Well, let's think about that, because the idea is, if I can get all cosines over here, if I can make all of this be cosines, I can let u be cosine and I have a du. Then I can do u substitution. Well, you can use your power reducing formula, because that sine squared can be turned into a cosine. So we don't necessarily need to reduce the power in this case. We need to get our sine into a cosine, so we can just use our basic Pythagorean formula. So when you're trying to figure these out, you really need to think about, where am I going? What's my plan of action to get there? Why does this work now? Or why will this work eventually? We've got u's. Or at least we can turn our cosines into u's. And you can do that at any point. You can keep kind of reducing or simplifying here, turning it into, you can do it anytime you want, but let's just try it. If I let u equal cosine of theta, my du is negative sine theta, right? And there's a lot of different ways you can go from this point. You can keep separating these fractions and get them as simplified as possible, meaning I could have 1 over cosine squared minus 1. However you want to do it, I'm just going to go ahead and turn everything into u's, because I think it's easier to start working with the u's as soon as possible. You need a negative, so you'll need a negative out front to do that, right? You need your negative out front, because you need your negative in here. Remember, when you distribute a negative with a difference, all you're really doing is flipping it around. It just makes it a little bit easier. So what's that going to give me? Negative integral of u squared minus 1 over u squared du. So I can now split it up. I can take u squared over u squared minus 1 over u squared, which is going to give me 1 minus u to the negative 2 du. And you can easily, so what's that? Go to the u. Because integrate 1, you go to u. Integrate u to the negative 2. That's going to raise up to negative 1. And then multiply by negative 1 is going to make it plus 1 over u to the negative 1, plus c. So u was cosine, so I have negative cosine u plus 1 over cosine theta plus c. So I'm going to keep going. Like I said, this lesson is literally just a bunch of integrals. So you can start to do is try them on your own and then come back and see how you do. So this next one I want to give you, let's move over to the tan secant pairs. Let's do tan of 3/2 x secant of 4x dx. All right, so write it out, take a look at it, and let's think about this. So that tan 3/2 x, that's just a little bit of a nightmare. We're going to leave that as it is. Let's play around with the secant squared. So think about that. Well, the integral of tan, the derivative of tan is secant squared. So it might be helpful in this problem to take secant to the 4th and turn it into secant squared x, secant squared x. That gives me a built-in du if u equals tan x. Now, we can't let u equal tan x yet because we don't have just a tan x. But what we do have is another secant squared x that we can apply one of the Pythagorean theorem identities to. Pythagorean theorem identities, PTI, Pythagorean theorem identities. Okay. What does that mean? Well, I keep my tan 3/2 x. Secant squared is 1 plus tan squared. And then I keep my secant squared x dx. As long as the rest of it is in terms of tans, at some point you can let u be tan, and you already got your built-in du. So that's what you're trying, that's kind of your goal from the beginning. Before we do that, we can distribute, make it a little bit easier. So this is tan to 3/2 times 1. Tan to 3/2 x plus tan squared. Remember, you were not multiplying, you were adding exponents. So it's 3/2 plus 2, which is 3/2 plus 4 over 2, which is tan to the 7/2 x. So now I can go ahead and let's let u equal tan x and du equals secant squared x dx. So all I'm integrating is u to the 3/2 plus u to the 7/2 du. That's it. It's literally what it goes down to. You can do your derivatives. It's u 3/2 goes up to 5/2, so it becomes 2/5. 7/2 goes up to 9/2, becomes 2/9, plus c, and then just go ahead and put your tan back in, and you're done. Plus c. Done. Okay? And it really doesn't matter what the exponent is on the tan. That's going to work. As long as if you have a secant to the 4th, that will always work. So a secant to the 4th with tan raised to any power could be square root of tan. It's going to work. So let's mix that up a little bit. Here's the problem. I don't have anything squared or to the 4th power that I can break up. I really can't get a secant squared out of secant to 3/2. So you need to forget the idea of putting everything in terms with tan and getting a secant. But maybe I can entertain the idea of putting things in terms of secant and then using tan secant as my du. So if I can get a tan secant pair together, then all I really need to do is deal with the secant part. All right, so in other words, instead of looking for that secant squared dx to become my du, I'm looking for tan secant to become my du. So then my u is just going to be a plain old secant. Let's try. Well, I've got a tan. Don't worry that it's 4x. It could be 4x, 2x, 3x. That part doesn't matter. As long as the key here is the 4x's are the same. All right, don't worry so much about that. It just means we're going to have a coefficient and probably a quarter out front somewhere at some point. So what do I need? I want to have, here, I'll put them in red. I know I can't get a secant squared out here, but maybe I can get a tan 4x secant 4x dx. If I can get that, I can work my way back. That can allow that to be du, and then I just need a secant for my u. Well, let's see what happens. Tan to the 4th was already there. I just moved it over. I took out a secant to the 1st power. Well, if I take out a secant to the 1st power, what would I need to multiply it by to get secant to the 3/2? I would just need to multiply that by a secant. Right? Think about that. We're working backwards. I have secant to the 1st power. I need to multiply it by another secant to get a 3/2 power, so I'm missing the 1/2. All right? So all I basically did is took this and broke it into secant 1/2 4x times secant 4x, because 1 plus 1/2 is 3/2. I did that so I can get that derivative that I need, and then it'll work. Because in doing that, I can now let, oh, wait a minute, u just be secant, I forgot the 4, sorry, that's a 4x. I can let u now be secant of 4x, and guess what du is? Well, it's secant (4x) times tan 4x times the derivative of 4x, 4. So I almost have the whole thing. The only thing I'm missing is a 4, which I can compensate by putting a 1/4 on the outside. And in doing that, I have 1/4 integral of u to the 1/2, don't forget the 1/2, du. I took that in crazy trig function, manipulated it so I got a u sub, and then it's just 1/4 u to the 3/2 times 2/3. So that's 2/3, so that ends up being 1/6 secant to the 3/2 of 4x plus c. Ooh, so let that one kind of sink in a little bit. And these start to kind of follow again the same pattern. I said this is going to be a bit of a long video, so if you can get the problem on your own, great. If not, use these as practice. So go ahead and try this one. There it is. Tan 2x times secant 2x dx. Again, you don't have a secant squared, so that's not going to work. If the secant was squared, we'd be done. U would be tan, u to the fifth, and we can just finish the problem. We don't have that. So, what do we need? We need to get, since we have this tan secant relationship, we know secant squared isn't going to work. We need that du again to be secant, in this case 2x tan 2x. All right, we got to figure that out. Well, that's fine. Let's just break it up. Instead of tan, let's break up tan to the fifth, tan to the fourth of 2x, and then tan 2x, because that'll get me my tan to the fifth. I really didn't do anything but break that up. I know what you're thinking, but wait a minute. The derivative of tan is not tan secant, so that's not going to work. We're almost there. I have a du here. I got that du I want. Yeah, that doesn't work because I can't, I would need a secant squared for that to work. All right, but maybe we can turn tan to the fourth because it's a nice even power. The powers are going to really make a difference on the approach you take in a lot of these problems. Oh, I can get, we know tan squared is simply, by Pythagorean identity, secant squared 2x minus 1. So tan, but I've got two of them. So I've got a tan squared times a tan squared, so that gets squared. And then you have remember, all you need is this piece just to have secants in it in order to do your u sub. Then we can change everything to u's and they're much easier to work with. So I can let u be my secant of 2x. Don't forget it's got to be secant of 2x. Du is tan 2x times the derivative of du, so you need a 2 out front. So I do need a 2 out front, and I need a 1/2 here. Ooh, 1/2. The 2 goes with that, becomes du, and I have u squared minus 1 squared du. Isn't that a much easier integral to work with than the original? And then, just do all your algebra magic. I'm not gonna, you can figure this out. C, and then just stick your secant back in. And don't forget, hold on, plus C. So you got a lot going on there. Again, I'm just going to keep going. You can pause videos at any time. And I know, we have a lot. So here's one. Tan cubed. Tan cubed. This is one of those where These are power reducing integrals, but we're going to work it out, and then I'll show you a formula that you can choose to memorize if you wish. We're just going to work it out. Kind of the same way, the same idea we've been doing. It's really not too much difference, but it's a little bit different. Because you're like, okay. Yeah, having a tan of anything isn't going to help you. Because I can take out a tan and have a tan squared. I can certainly break it up, and we may be breaking it up. All right? Sometimes you have to play around with these until you get to something that works. So yeah, we can break it up into tan. I'm hoping you're staring at this for a minute and you're thinking, yeah, but how does that help my use of? Because neither tan nor tan squared is the derivative of a trig function. And I've got a secant. So that really doesn't help me, does it? So then, honestly, at this point, start manipulating. I mean, just start manipulating. All right? I do know I can get a secant by turning tan squared into secant. So we can try that. So what's that going to give me? It's going to give me secant squared theta minus 1. I just turned tan squared into secant squared theta minus 1. Yeah, that still doesn't help me because the derivative of secant is secant tan, and the derivative of tan is actually secant squared, not secant squared minus 1. So you're like, all right, let me distribute it and see what happens. A lot of this is going to be trial and error. So we have tan alpha secant squared alpha minus tan alpha theta. Sorry, keep calling it alpha. You're like, well, wait a minute. It works really nicely if I break up the integrals. Right? Check this out. This one works. Right? U equals secant squared theta. No, sorry, that was wrong. U equals tan theta du equals secant squared theta. So what does that give me? Oh, it's all there. It's just the integral of u du. What's the integral of tan theta? So this is one that you're going to want to check out because watch this. Isn't tan theta, can't I just write that as, you might have done this, you probably did this in Calc 1. I got a u sub now. Look, always let u be the denominator. I need a negative, so that actually becomes positive. So that integral, because we separated them, is now integral. I'm going to use u's. You could use a different. You probably should use a different variable. So yeah, let's do that. We'll call them g's or something. I don't know, dg. Only because we're using u's in the other one. Doesn't matter. 1 over g dg. That becomes u squared over 2. This becomes ln of g. And just plug everything back in. So it's tan squared theta. I lost a half somewhere. Did I lose something? Nope, there it is. Over 2. I didn't lose anything. plus ln of cosine. Answer. So this was a tan. Simple tan to a power. I'll show you on your slides. We have this, whoops, wrong one, this one. Where whatever tan is, I reduce it down. So remember, we did tan, let me do a different color here. We did tan cubed x. Oh, so we get tan n minus 1 is squared over 2 minus, this is where it gets kind of tricky, the integral of tan minus 2 of tan x dx. So, this is called, these are our reduction formulas that you can choose to memorize. So the reduction formula for tan says reduce the power, divide by what you reduced by, subtract the integral of the power reduced by 2. So let's go back to our notes. Yeah, so I used trig properties. Sorry, it gets stuck sometimes. There we go. I use trig properties to get there, but theoretically, if you want to memorize the reduction formula, you reduce it, divide, minus, this is just the reduction formula for tan. So if you want to memorize these reduction formulas, you need to memorize them for all the trig functions. Minus the integral of, so was exponent of 3, subtract 2, tan x dx. You still need to do this piece right here. You're still going to have to work that out. So again, you're going to get the exact same answer. It is entirely up to you whether you choose to memorize reduction formulas or do the math. When you do reduction formulas, though, keep in mind that you have to sometimes do it a couple, or not that you have to do it a couple times, but sometimes when you that other integral, you still need to think through how to do the integral. So let's do what? Let's do tan to the 4th using reduction formula. We'll stick with tan. So integral of tan to the 4th, theta d theta, using a reduction formula. So the reduction formula states, go back, I'll show you, all right, let me erase. So it's a tan, and I want you to notice real quick, reduction formula for sine is quite complicated, so is cosine. Tan is a nice one because the reduction formula for tan is one of the easier ones to work out, but you can certainly memorize at least the sine and cosine and tan and secant ones if you choose to. Or, as you can see, these problems can still be worked out without them. But if I want to do reduction form, the reduction formula just states this goes down by 1. And then let's go back. So here's tan. Goes down by 1, subtract goes down by 2. The integral of going down by 2. All right, let's go back. We'll subtract, right? Yep. And that's the end. You got to remember each little part of it minus the integral of tan squared theta d theta. All right, so however you choose to do it, that's entirely up to you. We still got to take care of this integral of tan squared. So in other words, I'm not forcing you to memorize reduction formulas. You just got to work out properties a little bit more and use your u sub a little more if you don't memorize your reduction formulas. Again, entirely up to you. I still got to integrate that. Okay, which is, well, it's kind of easy to integrate because you can see that tan squared is squared theta minus 1. Oh, but the integral of secant squared is just tan theta plus theta plus c. All right, so there's a case where the reduction formula does save you a few steps. The part that it saves you is dealing with this initial tan theta secant squared piece. It kind of saves you from dealing with that, which is always going to come out to the same thing. All right. So there's a way you can use your reduction formula. So again, this chapter is all about the tricks we use. Let's take a look at, we're going to do 2 more. So I'm sorry the video is so long, but you can just flip through it and try different things with it. I mean, just go to the ones you try it or practice them. Pause and then go to the end. So here's one. This is where we can introduce. So secant theta by itself doesn't do anything. It doesn't do anything. This is getting incredibly creative. But getting creative works with solving integrals. Here's the thing. If I had a secant squared, integral of secant squared is just tan, right? If I had a secant times tangent, that's fine because the integral of secant tangent is then secant, right? So we have some relationships here. Back when you were in pre-calculus, when you were working through your proving trig identities, sometimes you had to introduce crazy things. That's the idea here. So what did I just say? Oh, if I could just have a secant theta and a tan theta, this just might work. Well, I can multiply anything by what number? Yeah, I can multiply anything by the number 1. Right? What does that give me in my numerator? Oh, secant squared theta plus secant theta tan theta over secant theta plus tan theta d theta. Yeah, I know I made the integral crazy, but guess what? If I simply let u be that denominator, guess what du is? The numerator. Look at that. That insane problem if you just thought about it creatively. Now, how are you going to know to do that? Well, you wouldn't, but now that you've seen the example, maybe you will, right? So here we go. Isn't that just going to be 1 over u du, which is ln of u plus c, which is ln of... Done. So one that seemed hard really wasn't. Here's another trick. I'm trying to show you these little tricks that come up. Here's another good one. I think this one actually brings in integration by parts, which is cool. Secant cubed. Secant cubed theta d theta. Integral of secant cubed theta d theta. So again, this is where you've got the two routes to go. You can totally memorize the power reduction formulas. We'll get to in a second. Or let's do the roundabout way first, and we'll double check it with the power reduction formula, okay? My roundabout way of doing this is, wow, maybe let's try... So again, I'm showing you what you would have to go through if you choose not to memorize all the power reduction formulas, because there is a power reduction formula for secant. For, any secant. If I do this, think about that. There's something we haven't used yet in this lesson, and that's our partial, sorry, not partial, integration by parts. Partial derivatives are at the end. They involve limits. We're not there yet. That's at the end of chapter 8. So our integration by parts. Integration by parts would lead us to believe, well, let u be the piece I can easily take the derivative of, and dv be the piece I can easily take the integral of. Well, I can easily take the derivative of that. I'm going to let that be u. And I can easily integrate that, so I'm going to let that be dv. All right? So in other words, I'm going to let u equals secant theta, and dv equals secant squared theta d theta. Du, we know, is secant theta tan theta. Oh, and v is just tan theta. So you're thinking, all right, well, this isn't too bad. But we'll go through the problem, then you can make that decision if you're going to memorize power reduction formulas. So, my integration by parts. Remember, do your little arrow thing. It helps. Boom. And then this way. Just do that. We ignore dv. Once we identify it, we don't really use it. Okay, u times v, which is just, hey, secant theta, tan theta. Okay, minus the integral of, well, it's going to end up being secant times tan squared, right? Yeah, we got two tans. Tan squared theta d theta. Okay. All right, well, I can put my tans all in terms of secant. So copy this part down. What does that mean? I can make tan squared be equal to secant squared theta minus 1, right? If I make that and I distribute it across, I end up with secant cubed theta, right? Minus, because remember this went to that. Okay, why is this important? Ooh, come up here. Yeah, you feel, in a way we feel like we're repeating ourselves because we have this and this, but this allows us to do a little fun algebra. Let me show you. Let me break this integral up first. It'll make it a little bit easier to see. Meaning I'm going to turn this into cubed theta plus integral of secant theta d theta d theta. I just split that into two integrals. Remember what this all equals. This all equals secant cubed theta d theta. Well, I can take this, right, and add it to the other side, which gives me two of them. I know, this is crazy. So now I have secant theta tan theta plus integral of secant theta d theta equals two integrals of secant cubed I can divide out my 2. And divide out my 2 everywhere, right? And I'm going to move this over here. So now I have the integral of secant cubed theta equals 1/2 secant theta tan theta plus 1/2 the integral of secant theta d theta plus c. We'll put our plus c in at the end. Why is that important? Because I believe I just did that. Yep, there it is. We know what the integral of secant theta is. I know. You're not going to necessarily memorize that, but you might be able to quick. We didn't even take that long to do it. If you remember how to do it, it'll come up again. It's just a natural log of secant theta plus tan theta. So it's 1/2 secant theta tan theta okay. Now, if I did a power reduction, oops, sorry. I would need to use the power reduction formula for secant, which means I would need to memorize it. It is, let's go through it. Reduce the secant by 2, multiply by tan, and then take 1 away. Whew. All right, what does that mean? Reduce it by 2. So remember, this was here, I'll write it in here. It was a secant cubed. So then it becomes secant, just to the first, right, because we're reducing by 2, over 3 minus 1 over 2. So there's our first part. Let's go back. Our first part is, oh yeah, 1/2. But you're going to memorize it. Tan theta. All right, what's the next piece? It's not going to say ln. Now I got to put, all right, remember I have 3, so this is subtract 2 is 1, subtract 1, 1/2. There's our 1/2 again. Integral of secant down by 2, which is just secant x dx. So in our case, it ends up being the integral So here's the thing. No matter which one you use, you still need to know this. So you got choices. You can memorize the integral for secant. We learned a couple new integrals today. We learned the integral for secant, and we kind of reviewed, because I think you did know it before maybe, the integral for tangent. And if you're really good at memorizing, you're done. You can do this problem in 2 steps by using your power reduction formula. So, you may have heard me in the other videos always talk about, I'll never really make you memorize a lot, because at the end of the day, it really is up to you. We were able to solve this whole thing with just that group of the Pythagorean, that was it. Integral by parts, all of that. We were able to solve this entire thing. You could also solve it in 2 steps if you memorize the formulas. That, honestly, I'm not even being sarcastic, totally up to you. You know yourself. Do what is best for you. You can even, so we did learn a couple, like all your integrals, but couple of the ones we did today, so a couple more, I'm not going to call them common integrals, but a couple things you did learn today is you learned the integral in doing one of our problems, an integral of tan x dx. Because remember, we showed, hey, you can turn tan x into the sine over cosine. Again, you might have done this in Calc 1. And when you turn tan x into sine and cosine, you end up getting basically 1 over u. When you integrate 1 over u, you get ln. So it actually is the negative natural log cosine x plus c. All right. Another one we did is the integral of secant x. And the integral of secant x, we just did a whole bunch of times, is ln of secant theta plus tan theta plus c. And these are pretty important. You can integrate them using any of your rules, of course. But I want to take the tan x one a little bit further, because if you, let me do it in red up here. If you took the negative of ln, right, cosine x, you know with a natural log, you can move it as an exponent. That's the same as the ln cosine x to the negative 1, right? Well, what's 1 over cosine? Is it 1 over cosine secant? So, yes, the integral of tan is negative natural log of cosine x, or, which is also equal to natural log of secant x plus c. So, they're actually not too difficult to memorize, those two. They will come up. You don't need to show them again. All right. The other thing that was kind of added to this lesson, besides all our tricks with using our trig identities, is these, right? So these are in the notes in Canvas. They also provide you with a whole bunch of tricks. If something's positive or negative, you can take a look at them on your own. This is your choice. You choose to memorize those or not. I will leave that up to you. All right. I went through a bunch of problems. Please practice these. Practice, 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 and then they kind of become second nature. All right. And that's 8.2.